Have you ever stopped to consider the hands of our most famous celestial visitors? Think of the gentle, glowing finger of E.T. reaching out, or the slender, mysterious hands of the Greys so often depicted in tales of encounters from beyond our world. There are 4 fingers, not 5 like ours, but 4. It is a curious and remarkably consistent detail that populates our collective imagination of what life from another planet might look like. This small but significant choice is not merely an artist's whim or a filmmaker's convenience. It prompts a deeper question. Why should this specific design be so prevalent? On our planet, the 5-fingered or pentadactyl limb is the dominant blueprint for terrestrial vertebrates. From the flipper of a whale to the wing of a bat and our very own hands, this 5-digit pattern has been the standard for hundreds of millions of years. It is a legacy handed down from our ancient fish-like ancestors who first crawled from the sea. We tend to see our 5 fingers as the default, the perfect number for grasping, manipulating, and interacting with our environment. But evolution is not a march toward a single perfect form. The process of evolution is, at its core, a ruthless accountant. It keeps a strict budget for energy. Every feature an organism develops, from the feathers on a bird to the very fingers on its hand, comes at a biological cost. It takes a significant amount of energy and complex genetic instruction to grow and maintain each part of the body. If a feature does not provide a benefit that outweighs its cost, natural selection will often favor a simpler, more streamlined design. A 5th finger, if it is not providing a crucial advantage for survival, becomes a luxury, an unnecessary expense that the relentless pressures of nature might eventually edit out of the genetic code. Imagine an alien world with slightly higher gravity than Earth. On such a planet, every ounce of body mass requires more energy to move and support. Shedding a digit, along with its associated bones, muscles, nerves, and tissues, could represent a small but meaningful energy saving. When multiplied across an entire population over thousands of generations, this tiny efficiency can become a powerful evolutionary advantage. The 4-fingered hand, therefore, might not be about what is missing, but rather about what has been perfected through subtraction, resulting in a creature that is better adapted to the physical laws of its home. The development of a limb as complex as the human hand is a marvel of biological engineering, but it is also fraught with potential complications. The genetic signaling required to form 5 distinct and properly articulated digits is incredibly intricate. During embryonic development, a delicate cascade of genes must activate in perfect sequence to ensure each finger grows to the right length, in the right place, with the right connections. A simpler system, one that only needs to produce 4 digits, could inherently be more robust and less prone to developmental errors. From a purely biological standpoint, a 4-fingered structure can be a stronger and more stable one. Consider the mechanics of a grip. When we grasp an object tightly, the primary force is often exerted by the thumb, working in opposition to the fingers. A hand with 3 strong fingers and an opposable thumb can, in many situations, generate a more powerful and secure grip than a hand where that same force is distributed across 4 weaker fingers. By reducing the number of digits, the resources used to build them can be reallocated, resulting in each remaining finger being thicker, with stronger bones and more powerful muscles. This concept is not alien to our own world. Think of the panda's thumb, which is not a true finger at all, but a modified wrist bone. It evolved to provide a simple, strong anchor for holding bamboo. It demonstrates that nature can innovate to create effective grasping appendages without adhering to the 5-finger rule. An alien species might have followed a similar path, finding that a 4-digit configuration provided the perfect balance of dexterity and power for its needs. One of the most profound lessons from the natural world is the principle of convergent evolution. This is the phenomenon where unrelated species, facing similar environmental challenges, independently evolve similar solutions. The wings of a bird, a bat, and an insect are a classic example. They are structured very differently, originating from different ancestral body parts, yet they all solve the problem of flight in a remarkably similar way. This suggests that there are certain physical and biological laws that constrain and guide evolution toward a finite set of successful designs. The laws of physics are the same everywhere in the universe. Applying this logic to life on other planets, it is entirely conceivable that a 4-fingered hand is one of these optimal solutions, a sweet spot in the evolutionary landscape for intelligent, tool-using life. Just as flight has emerged multiple times on Earth, perhaps the 4-fingered manipulator has emerged on countless worlds across the galaxy. It may represent a common, convergent endpoint for species that need a balance of dexterity for tool use and strength for interacting with their physical world. It is a design that is complex enough for manipulation, but simple enough to be strong, efficient, and developmentally stable. Therefore, the next time you see a four-fingered alien in a film or read about one in a story, do not dismiss it as a failure of imagination. Instead, see it as a reflection of sound biological reasoning. The creators of these beings are, perhaps unconsciously, tapping into these fundamental principles of evolution. They are presenting us with a form that is not arbitrary or fantastical, but one that could very well be shaped by the same universal forces of efficiency, adaptation, and physics that have governed the story of life on our own planet. The alien hand becomes a symbol of a universal truth, that life, wherever it arises, must find clever solutions to survive. Ultimately, this line of thinking invites us to look beyond the hands and consider other common alien traits. Why do so many have large eyes? Perhaps they evolved on a dim world orbiting a distant star. Why are they often depicted as slender? Perhaps this is an adaptation to a high-gravity environment. The biology of fictional aliens is a wonderful playground for the mind, allowing us to explore the endless possibilities that evolution could create across the cosmos. It reminds us that if we are ever to meet life from another world, it will be the product of its own unique history, yet shaped by rules that are familiar to us all.